Hi everyone, in this video solve problem 38 from chapter 9 from the book of Thermodynamics Engineering Approach by Cengel. Here is a statement of the problem. An ideal Otto cycle has a compression ratio of 7 at the beginning of the compression. The beginning of the compression process P1, that is 90 kilopascal. P1 initial temperature, that is 27 centigrade. Volume V1, that is 0.004 meter cube. Maximum cycle temperature is 1127 centigrade. For each repetition of the cycle, calculate the heat rejection, the network production. Also calculate the thermal efficiency and mean effective pressure for this cycle. Use constant specific heat at room temperature. And these are the answers. So let me write what data that is given in the statement. Compression ratio, as we know that is given, and it is equal to V1 divided by V2. V1 is the maximum volume of the cycle, V2 is the volume that is compressed, and it is equal to 7. The initial temperatures 1 centigrade at 273 with it to convert into Kelvin, and it will be equal to 300. Pressure P1 is 90 kilopascal. Maximum temperatures of the cycle, that is T3, and is 1107 centigrade. Add 273 with it to convert into Kelvin, and it will give you the values of 1400 Kelvin. The initial volume V1 that is given 0.004 meter cube. So what are our required data? We need to calculate the heat rejection, the network production W net, and the thermal efficiency of this, and also the mean effective pressure. Toward its solution, let me draw the PV diagram of the Otto cycle so you can clearly understand its concept. So first is the compression process from 1 to 2, isentropic compression, then constant pressure heat addition process, Qn, let's say, then isentropic expansion. This is 1, 2, 3, and then constant volume heat rejection process is Q out. Also you can say Q rejection. So first process 1 to 2, then 2 to 3. Process 1 to 2 is isentropic compression. That's why volume decreases from V1 to V2, and the pressure increases from V1 reaches to V2. Then heat additions at a constant volume is taken place, and the pressures and temperatures is increases. It is 3, and the maximum cycle temperatures 3 is reached at this point, and it is given, that is 1400 Kelvin. Then isentropic expansion from 3 to 1 is taken place. 4 to 1 is heat rejection process at a constant volume. Remember, the volume V1 is equal to V4, and the volume V2 is equal to V3 because it is taken at a constant volume. V1 is the volume before compressions, and V2 is the volume after compression. So we can say that the compression ratio is equal to V1 divided by V2, and it is also given in the statement, that is 7. Now come towards solutions. I hope you understand all the concept that is required during this Otto cycle. If still there is any confusion, you can ask in the comments. Now come toward its solution. Before starting the solutions, we need some constant, that is Cp value is 1.005 kilojoule per kg Kelvin. The value of R value, that is 0.287 kilojoule per kg Kelvin. The value of Cv, that is 0.718 kilojoule per kg. Consider the process 1 to 2, it is isentropic compression. Then we can say that it's isentropic compressions. Then we know that 2 divided by T1 is equal to V1 divided by V2 to the power gamma minus 1, and the value of gamma is 1.4. For air, we can say that T2 is equal to, what is T1 value, that is 300 Kelvin, and V1 divided by V2 is equal to 7. Gamma value is 1.4 minus 1. So after solving this on calculator, you will get the value of T2, and it is equal to, let me solve this on calculator. And it is 653.4 Kelvin. Now consider the same process 1 to 2, we can also say that V1 divided by T1 is equal to V2 divided by T2. We are interested to find the P2. Multiply with T2 and divide with V2 both sides. T1 times into T2 divided by T1 multiply V1 divided by V2. This V1 divided by V2 is equal to 7 and T2 divided by T1 value is given. We have to put that and you will find the P2 value. Now consider the process 2 to 3 that is taken at a constant volume and heat addition is taken place. This is process 2 to 3 that is taken at a constant volume. We can say that P2 V2 divided by T2 P3 V3 divided by T3. Rearrange this equation for P3. Process 2 to 3 is taken at a constant volume. We can say that V1 V2 is equal to V3, then it will be cancelled out, and rearrange this equation for P3. What is T3? That is maximum cycle temperature, is 1400 Kelvin. What is P2? That is 1372. After solving this on calculator, you will get the 3 value and it is 2940 kilopascal. Now consider the process 3 to 4, that is isentropic expansion. This is 3 to 4 isentropic expansion and will give you the workout. You can say that T4 divided by T3 is equal to V3 divided by V4 power gamma minus 1. Also we mentioned earlier that V3 is equal to V2 and V4 is equal to V1. And also the compression ratio V1 divided by V2, that is equal to 7. So rearrange this equation for T4. T4 is equal to T3 into V3 is V2 divided by V4 is V1 into gamma minus 1. We know that V1 divided by V2 is equal to the compression ratio gamma, and so here if you see that it is V2 divided by V1 and it's reciprocal of V1 divided by V2, so this V2 V1 is basically equal to 1 over 7. Now just enter the value of T3 and its value is 1 over 7. These equations and you will get the T4 value. We need to find the mass of the working fluid by the equations P1. V1 is equal to mR P1, divide both sides with R T1 and you will get the equation for M, mass of the working fluid during this Otto cycle. What is P1? That is 90 kilopascal with initial volume, that is 0.004 divided by the value of R, that is 0.287, and then the value of T1, that is 300 Kelvin. After solving this, you will get the mass 0.004. Now the heat that is rejected is Q out and it is equal to mass of the working fluid CV and change in temperatures delta T. The value of CV and change in temperature, that is equal to T4 minus T1. This is the M value, that is 0.0048, and that is equal to 1.03 kilojoule. Next is to find the heat that is added process 2 to 3 and it is equal to mass of the working fluid CV values and change in temperatures from process 3 to 2. Mass of the working fluid is After simplification on calculators, you will get the heat that is added during this cycle or the heat that is supplied, that is 2.241 kilojoule. Now the network output is equal to Q in minus Q out. What is Q in? After solving this, you will get the network output, that is 1.21 kilojoule. Next is to find the thermal efficiency. Thermal efficiency is equal to the network out divided by heat supply, that is Q in. So what is network output? 1.21 divided by the heat that is supplied, 2.241 multiplied with 100, and you will get the thermal efficiency of the cycle, and it is 54% almost. The final requirement of this problem statement is to find the mean effective pressure. You know that mean effective pressure multiplied by change in volume is equal to network output. Now the change in volume need V1 and V2 values, and value of V1 is already given. It is 0.004 meter cube, and compression ratio is also given, that is V1 divided by V. Then we can say that V2 is equal to V1 divided by 7. 0.004 divided by 7 give you the value of V2. It is V1 value. I just simply put the values of V1, V2 and the network what produced. Its subtractions will give you the value of 0.00343. Divide both sides with 0.00343. That will be cancelled out with, and that is 353 kilopascal. And this is our final answer. I hope you understand. If still there's any confusion, you can ask in the comment section. Subscribe my channel if you haven't subscribed yet.